everyone. This is the 31st video for mathematical methods in economics, and the topic we will be covering in this video is sequences and series. This is actually a vast topic in mathematics, and what we do as economists is probably just scrape the surface. But nevertheless, sequences and series find wide applicability in economic analysis in areas such as finance, then forecasting, or while evaluating long-term economic trends and many more such areas. We will begin this discussion by talking about infinite sequences first in this first part of the video. So, an infinite sequence, or simply a sequence, is a listing of numbers. It is a list of numbers A1, A2, A3, A4 and so on, continuing indefinitely. And here these A's are known as the terms of the sequence. 2 points are in order here, 2 points of discussion. One, the first point here is that I am here referring to, in the entire first part of the video here, we will be talking about an infinite sequence where you have an unending succession of numbers. Okay. This is as against a finite sequence where you have a finite set of numbers. So, we will be focusing only on infinite sequences. Our infinite sequence here takes the format A1, A2, A3, A4 and so on, where this continues indefinitely. And here A1 represents the first term, A2 the second term and so on, A3 is the third term and so on. And if you notice here, there is a pattern. There is an order or pattern in the way we have listed our sequence of numbers. So, if you look at the subscript of the A's here, the subscript here it denotes the position of each term. So, if the subscript is 1, then I am talking about the first term. If the subscript of A is 2, then I am talking about the second term. So, the subscript, it acts like an index with which we are indexing the particular element in the sequence. Further, we can also highlight what is known as a general term in the sequence. This is represented by A sub n, and this general term actually plays a very important role in our analysis here, because the general term, it establishes a rule or a function, as we will see in a bit, which then helps us understand what the terms of the sequence look like. Okay, so let's take a look at a few examples of sequences. The first sequence that I have shown here on this slide is one which starts with a 2, then you have a 4, a 6, an 8 and so on. So, this continues indefinitely, and if you notice here, there is a pattern to the terms, so that each term can be written as 2 times n. Right, n here is taking on the values 1, 2, 3, basically the positive integers or the set of natural numbers. And if you notice here, if I put n equal to 1, I am going to get a 2. If I put n equal to 2, I am going to get a 4. If I put n equal to 3, I am going to get a 6 and so on and so forth. So, this general term helps us unravel the terms of the sequence. Similarly, you can look at this sequence. This is another example of an infinite sequence where the general term is 1 by n, and here again we are going to cheat a little bit. So, we can use this general term to unravel all the terms of the sequence, at least the first couple of terms, so that when n is equal to 1, you get a 1, then you have a half for n equal to 2, 1/3, 1/4 and so on, right? And there is another example that I have here for you, where the general term is 1 by 3 to the power n, which then generates the sequence 1/3, 1/9, 1 by 27 and so on and so forth. You can also go the other way around. So, you can start by looking at the sequence of numbers. You have 1/3, 1/9, 1 by 27, and then you can judge what the general term of this sequence will look like. Now, because in this video, in the second part, I will be talking about series, let me at the outset tell you the distinction between a sequence and a series. Now the sequence, if you look at all the sequences that we are considering here, sequences are lists of numbers, okay. So we are just listing out the numbers A1, A2, A3 and so on and so forth. But when we are looking at a series represents the sum of the numbers in the sequence, okay. So the difference is a sequence is a list of numbers, whereas a sequence is a sum of the numbers in the sequence. So if the sequence is A1, A2, A3 and so on, then this corresponding series would be A1 plus A2 plus A3 and so on. Okay. Now, because we are talking of the general term here, which we said it establishes the rule or the function based on which we can get the terms of the sequence, we can actually think of a sequence as a function which sends 1 to A1, the number 2 to A2, the number 3 to A3 and so on. In general, the number n is mapped onto the number an. So what do you notice here? If I think of this as a function where my domain is 1, 2, 3 and so on till n and so on, which is nothing but the set of natural numbers or the set of positive integers or your counting numbers. So here we can think of a sequence as a function where the mapping is from the set of positive integers to the elements of the sequence A1, A2, A3 and so on till an and so on. That is an infinite sequence. So to look at an example, we can think of a function f of n which is given by 2 times n, and here I am trying to replicate the first sequence I showed you on the previous slide. So here n, because the domain is the set of positive integers, so n takes on the values 1, 2, 3 and so on. And our function here, I have cheated here in the sense that I have taken the general term because that helps us generate the terms of the sequence. So my f of 1 would be 2 because I am going to put n equal to 1 here, and that is going to give me a 2, f of 2 will be 4, f of 3 will be 6 and so on. So the resulting sequence becomes 2, 4, 6, 8 and so on. Right. So let us define an infinite sequence. An infinite sequence is a function whose domain is the set of positive integers. I hope this is clear to you, and let us move on now. Right. Now, before I move further in the discussion, let me also bring in some notation for sequences, because we have listed out our numbers as A1, A2, A3 and so on. In a compact form, we can use this notation where we write the general term of the sequence A sub n in braces, in curly brackets, and this then represents the sequence A1, A2, A3 and so on. If we want to write an alternative, use an alternative notation, we can also specify that n goes from 1 to infinity, but that is not needed because it is understood that if you have an infinite sequence, the n's would be the set of positive integers. So you can simply do with this notation, which we are going to use for this video, which is where we just write the general term in curly brackets, and that then represents a sequence. Let us just see how that notation works. So my first sequence is, I am calling it A sub n, where the general term is 2 times n, and this then generates a sequence 2, 4, 6, 8 and so on. Similarly, I have given you another sequence here, which is 1, where the general term is 1 by n, and that is to say we have the sequence 1, half, 1/3, 1/4 and so on. So do you see, this is a very compact way of writing that entire sequence. Similarly, let me give you a new example now. If the general term is minus 1 to the power n plus 1 times 1 by n, here if n is 1, you can see here that every time n is an odd number, n plus 1 would be even, so that the coefficient would be positive. So for every n equal to 1, 3 and so on, your coefficients would be positive, and you have 1 by n. So your sequence becomes 1, minus half. So if n is 2, then it becomes minus 1 to the power 3, so that you have a negative sign in front of half, then 1/3, minus 1/4 and so on. Then I am also looking at this sequence. This is another interesting aspect where I have the sequence 10 times minus 1 to the power n minus 1. Here we see that for example, if n is 1, then I'm going to have the first term being 10. Then for the second term, n is equal to 2, so I'll have a negative sign in front of 10. And here we see that this sequence oscillates between 10 and minus 10. Okay, now moving forward, a main theme around which our discussion is going to be centered in this video is that of convergence and divergence. Whether we are looking at a sequence or a series, a main theme or the main question of interest that we are going to address is whether our sequence converges or not. And one way of looking at whether a sequence converges or not is to look at the sequence graphically, where I look at where I plot n on the in the horizontal axis, and I plot the elements a sub n on the vertical axis. Okay, so if I look at the sequence 2, 4, 6, 8, and so on, and I've plotted these points for you, you can clearly see that this sequence, the terms are becoming larger and larger in the sequence, and here we say the sequence diverges. Basically, again, it's a general term that gives you a hint as to whether the sequence converges or not. Let's look at some more examples, and then we'll set up the mathematical definition for convergence and convergence or divergence of a sequence. Now look at this sequence. Here we have a sequence where the numbers are 1, half, 1/3, 1/4, and you can see here these numbers, these points, the numbers are going down steadily, and as n approaches infinity, right, we can see that this sequence is approaching 0. And here I am also taking help from this general term, because you can see that as n approaches infinity, this general term 1 by n in the limit will tend to 0, and this is exactly what this sequence is telling us, a sequence of numbers. This is exactly what is happening here in the graph, where the numbers are tending to 0 in the limit. And this is then the kind of definition that we will be building up mathematically, where we look in the limit as to where this, what number, if any, is this general term tending to for convergence. Okay, so in this case, the sequence converges to 0. Now look at this sequence. We have 1, minus half. So for n equal to 1, I have a 1, then minus half, then 1/3, minus 1/4, and so on. So here you see that the sequence is oscillating, but the nice part is that the oscillations dampen as n approaches larger and larger numbers, or as n approaches infinity. And this is also something that the general term is reflecting, because as you can see here that as n approaches infinity, 1 by n will tend to 0. So we have a sequence here, even though it's oscillating, the oscillations are becoming smaller and smaller, and this sequence also converges to 0. It need not be necessarily 0, the point of convergence. It could be some other number also, as we will see in the examples that we have, but at least for now, this is what is happening. Okay. This is the last example for the graphs, where we have a sequence which is oscillating between 10 and minus 10. So for n equal to 1, you have a 10, then minus 10 for n equal to 2, and so on. So you can see that you have these oscillations, but then this is not, the terms are not going to any, they're not converging to any single value in the limit. So in this case, we do not have convergence. The sequence does not converge to a single number. Ultimately, we are interested in whether the sequence of numbers converge to a single number, right, as n approaches infinity. That is the idea of convergence. And now we can look at the mathematical definition of convergence. A sequence a n is said to converge to a number L, right? And here we are looking at the general term. The sequence converges to a number L if in the limit a n, the general term, tends to the number L as n approaches infinity, or the limit of a n, the general term, as n approaches infinity is L. So basically, we are looking at whether the sequence tends to a single value, a unique real number for convergence. And here, as you can see from this definition, if this sequence does not converge to any real number, then we say it does not converge, or it is said to diverge. Okay. Now, let us look at a few examples to see if we have picked up the concepts that I have just outlined in the last couple of minutes. So, this example requires you to write down the first 5 terms of the sequences that are given to you and then examine them for convergence. So, here you have minus 1 to the power n plus 1 times 1 by n, and we have seen that this sequence is 1 comma minus half, comma 1/3, comma minus 1/4, comma 1/5. So, these would be the first 5 terms, and clearly because the general term 1 by n, in the general term 1 by n tends to 0 as n tends to infinity, we say that the sequence converges to 0. In this sequence, we have the general term is 5 plus 1 by 5 to the power n. So, the first 5 terms of the sequence are, and here because these are the first couple of questions that we are doing, that is why I am asking for you to write down the first 5 terms of the sequence so that you understand the pattern of the numbers. Right. So, in this case, the numbers are 5.2, 5.04, you can just substitute for the n's, you get 5.008, 5.0016 and then 5.00032. And here you can clearly see that 1 by 5 to the power n is going to tend to 0 as n tends to infinity. So, in the limit the sequence will converge to 5. Okay. Part C of the question here gives a sequence where the general term is n squared minus 1 divided by 3n minus 2, which then gives us a sequence where when n is 0, where n is 1, you get a 0 as a first term. Then when n is 2, you have 4 minus 1, 3 in the numerator, and when I put n equal to 2 in the denominator, I get 6 minus 2, which is a 4, so 3 by 4, and similarly you have 8 by 7, 15 by 10 and 24 by 13 as the first 5 terms. Okay, to understand if the sequence converges, I will have to see what happens to the general term as n tends to infinity. And in this case, if you notice, the general term is n squared minus 1 divided by 3n minus 2, which I can write as, I can take n squared common in the numerator. So, I get n squared times 1 minus 1 by n squared, and in the denominator I have n times 3 minus 2 by n. The one of the n's will get cancelled in both the numerator and the denominator. So, that my numerator now becomes n minus 1 by n. If I just take the n inside, one n that is left in the numerator, if I take it inside, I get n minus 1 by n, and in the denominator I have 3 minus 2 by n. Okay. And clearly you can see here, because of that n in the numerator, see, as n tends to infinity, 1 by n and 2 by n will tend to 0. But you still have this n in the numerator, so that this general term a sub n will tend to infinity as n tends to infinity, and by definition then this sequence diverges. Okay. In the next example, we are asked to test for convergence. Now, I am not going to ask you to write down the terms. You should now get into the habit of testing for convergence by just looking at the limit for the general term as n approaches infinity and arriving at your result. So, here the general term is 1 plus minus 1 by 2 to the power n. Here the result will be that if I take the limit of 1 plus minus 1 by 2 to the power n, as n tends to infinity, this fraction here minus 1 by 2 to the power n will tend to 0, so that this entire general term will tend to 1, and therefore we conclude that as n tends to infinity, the sequence converges, and in particular it converges to 1. Let us take a look at the next sequence, where the general term is given by n squared divided by n squared plus 2. And here basically, if you remember your limits, we are basically taking limits at infinity, right. So, if I take the limit at infinity for n squared divided by n squared plus 2, first of all, a convenient way of writing this would be to write divide both numerator and denominator by n squared, so that I get 1 divided by 1 plus 2 by n squared, and clearly you can see that as n tends to infinity, this ratio will tend to 1. So, here again the sequence converges. Another 3 examples to go for this particular question. Let us look at square root of n. Now, clearly square root of n, you must be familiar with the graph also. The terms get larger and larger as n increases. So, this is a sequence that diverges. Similarly, if we look at 7 minus 5n, the sequence 7 minus 5n, this is a sequence that will tend to minus infinity as n tends to infinity. Therefore, this sequence also diverges. Finally, look at this sequence, 1 plus minus 1 to the power n. Now, here if we just get a sense of what the numbers look like, if n is 1, this would be a 0. If n is 2, this would be 2, because minus 1 to the power 2 would be 1 and 1 plus 1 is 2. So, basically you are going to get a sequence which is oscillating between 0 and 2, and in this case a sub n will not have a limit. So, we conclude that the sequence does not converge to a single value. Ultimately, we are concerned with whether the sequence converges to a single value as n tends to infinity, and that is then the condition, the criterion for determining convergence. Otherwise, the sequence diverges. Okay, this is an interesting example which kind of makes things visual also, and you will get a better sense of things. Here we have that for n greater than or equal to 3, suppose a sub n represents the area of a regular n polygon inscribed in a circle with radius 1. As you would know, if you have a circle with radius 1, then the area of the circle would be pi, right? Now, let us get a sense of what this a sub n represents. First of all, if you notice here, if n is equal to 3, a sub 3 would represent the area of a triangle. If n is equal to 4, a sub 4 would represent the area of a square. Now, note here that this kind of a calculation does not make sense for n equal to 1 or 2. So, that is why we are starting with n equal to 3. Okay? The question then asks you, does the sequence a sub n converge? And if it does, then to what value does it converge? Let us get a sense of things in a visual sense here. If you look at A3, A3 is nothing but the area of a triangle which is inscribed in a circle with radius 1, and it is shown here on the slide. Similarly, if I look at A4, A4 would be the area of a square. A4 would represent the area of a square which is inscribed in a circle with radius 1. Similarly, A sub 5 would represent the area of a pentagon which is inscribed inside this circle with radius 1. Let us just take a look at these three pictures together and see what is happening. As n increases, what do you notice? The difference between the area of the polygon and the circle, do you see that? That becomes smaller and smaller. So, if you see the area shaded in blue in each one of these three pictures, that area shaded in blue is becoming smaller and smaller, which is to say that a sub n in the limit will tend to pi, which is the area of the circle with radius 1 as n tends to infinity. You can think of this intuitively or through this picture here, and this is the result that we get, and here the limiting value will be pi, where pi, as you all know, is 3.1415 and so on. It is an irrational number. Okay, let us take a look at this sequence as well. Now, this is a sequence whose general term is a sub n equal to 1 plus 1 by n to the power n. Now, the proof of this particular sequence we are going to do later when we cover exponential functions, but let us get a sense of what the terms of this sequence look like. So, again I will take n going from 1, 2, 3 and so on, and I have taken a lot of big numbers as well here. The corresponding values that I get for these n's, where I calculate 1 plus 1 by n to the power n for these given values. So, when n is 1, I get a 2, when n is 2, 2.25 and so on. When n is 100, I get 2.7, when n is 10,000, I get 2.7181, when n is 1 lakh, I get 2.7182, and basically what you can see here is that in the limit as n tends to infinity, 1 plus 1 by n to the power n, it tends to this irrational number e, which we are all familiar with. It is one of the most popular constants in mathematics, and this is a kind of a limit that we will look at when we cover exponential functions, but I thought it would be good to put the result here so that you have a sense of things when you cover that particular topic. So, we will be ending the discussion on infinite sequences at this point. I will leave you with an interesting sequence which you may have heard about, which is the Fibonacci sequence. If you have an interest in studying patterns in nature, or if you've read the Da Vinci Code, or if you are interested in art, this is a sequence that you would associate with. So, what exactly is the sequence? This is one where you start with 1, then you go to 2, and basically now the numbers that we will have, each number will be generated as a sum of the previous 2 numbers. So, but if I start with 1, then go on to 2, then the third number will be 3, the fourth number would be 5, right? Then the next number would be 8, then it will be 8 plus 5, 13, right? Then it will be 8 plus 13, 21, and so on. So, each number is generated as a sum of the previous 2 numbers, and this is the Fibonacci sequence, nothing to do with what we discussed here in this particular video, but it's an interesting sequence that you might be interested in. And that's all for this part of the video. Thank you very much.